How do power plant grounding systems actually work? Imagine a lightning strike hitting a power plant. What keeps that surge from frying everything inside? That's where grounding systems come into play, acting like the safety net for electrical systems. They are designed to keep everyone safe, protect equipment, and keep the power flowing smoothly. When you think about power plants, renewable energy sources like solar or wind farms, and how electricity gets distributed, grounding is a key part of the puzzle. So, what exactly is grounding? It's creating a direct connection between parts of the electrical system and the earth. This connection helps stabilize voltage levels so that they don't fluctuate wildly. It also provides a safe path for fault currents, those unexpected surges caused by faults or short circuits, to flow back to the source. This way, protective devices like circuit breakers can quickly disconnect the faulty part, stopping damage and preventing fires. There are two main types of grounding in power plants. System grounding connects the neutral point of the transformer or generator directly to the ground. This sets a reference point for the entire system and makes fault detection easier. Equipment grounding, on the other hand, links metal enclosures and non-current carrying parts of electrical equipment to the ground. This prevents these parts from becoming energized and causing electric shocks. When a fault happens, say a live wire touches a metal enclosure, the grounding system provides a low-resistance path for the fault current. This allows the current to flow back to the source quickly. Protective devices sense this surge and trip, isolating the problem. The lower the resistance between the grounding electrode and the earth, the better the fault current can dissipate. Engineers test soil resistivity beforehand to ensure the grounding grid will work effectively. Neutral grounding methods influence how the system reacts to faults. Solid grounding connects the neutral directly to earth without any resistance, allowing large fault currents that are easy to detect. Resistance grounding adds a resistor between the neutral and ground, limiting fault current and reducing stress on equipment. Reactance grounding uses an inductor instead of a resistor, helping control transient overvoltages. Ungrounded systems do not intentionally connect the neutral to earth, but they can develop dangerous overvoltages during faults, so they are less common today. Designing a grounding system involves considering voltage levels, soil conditions, and safety standards. For high-voltage systems over 1,000 volts, the grounding resistance must often be less than half an ohm. Grounding electrodes are usually made of copper or copper-clad steel and buried deep enough to reach moist soil, which conducts electricity better. The entire grid must be continuous and capable of handling the maximum fault current without overheating. Regular testing and maintenance, like measuring ground resistance and checking for corrosion, keep the system reliable over time. In power distribution, especially where underground cables meet overhead lines or enter substations, proper grounding ensures safe fault current flow and smooth operation. Standards set by national and international agencies specify maximum touch and step voltages to protect people from electric shocks. Following these rules is essential for safety and legal compliance. In essence, power plant grounding systems work by creating a safe, low-resistance path for fault currents to return to the source. They help detect faults quickly, protect equipment from damage, and keep personnel safe. Good design and regular maintenance ensure these systems work effectively, making the entire power network safer and more reliable.